Hello and welcome to the Energy Use and Efficiency unit of Phys 1101, and we're going to look at two ideas, power and efficiency, which are particularly useful when you're talking about energy in many contexts, not just in physics. We're going to start by looking at something that might still be causing you some confusion. Think about pushing a heavy box across the floor. And let's say you're doing it at constant speed and in a straight line. So we know that F net is 0. And so the force that you are exerting has to be equal in magnitude to the kinetic friction. Okay, so we've known this sort of thing for quite some time in this course. And notice that nowhere in here is there any dependence on the speed at which you push the box. The force you are exerting is the same whether you're pushing the box fast or slow, as long as F net is 0. But you will have observed that in this sort of situation you get tired more quickly if you push it fast than you do if you push it slow. And so it might be a little hard for you to believe that in fact the force you exert is the same whether you push the box fast or slow, because surely you would be getting tired more quickly because you're exerting a bigger force, right? That's sort of a logical thing to think, although it turns out to be wrong. So first of all, let me assure you, the force you're exerting is the same whether you push the box fast or slow. As difficult as that may still be to believe because of your experience of getting tired more quickly if you push it fast. And so clearly we still have something here that we need to explain. Perhaps it won't surprise you to find out that to understand what's going on here, we need to think about the energy. So let's be a little more specific. Here you are pushing this box across the room, and let's say you're exerting a constant 300 Newton force on it to keep it going at a constant speed, and the distance that you travel is 10 meters. Then the work that you do on the box, and note I put the force that you're exerting parallel with the direction of motion, so we don't have any cos theta to deal with here, right? So it's just going to be the force that you're exerting times the magnitude of the displacement. And that's simple. That is 3,000 joules. Now, again, this is independent of how fast you push the box. That amount of energy is the amount of work you do whether you push it fast or slow. It doesn't matter. But now let's think about something else. If you push it across the floor slowly, then the rate at which you do work, rate of work done. Let's say you take a time of, I don't know, 10 seconds. You're pushing the box at 1 meter per second across the room. That's actually a reasonable walking pace. Then the rate at which you are doing work is that you do 3,000 joules worth of work in 10 seconds. And so this is 300 joules per second. Whereas if instead you do this all at a brisk jog or something, so that let's say you take 3 seconds, which means you're going somewhat over 3 meters per second, which is easily done, right? That's a fast jog, say. Then the rate is 3,000 joules over 3 seconds, and that's now 1,000 joules per second. Well, you might say, so what? But think about what's going on here. To do this work, your body is having to convert chemical energy stored in your cells. It's energy coming from the food that you've eaten. And it's having to convert it into this work. And it all ends up as thermal energy, right? So our overall transformation here, because you're just working against friction, right? Everything's kinetic energy is staying the same, nothing's moving up or down. So this is all chemical energy stored in your body going to thermal energy. So this means that the rate at which your body is having to convert that energy, in other words, the rate that your metabolism is having to run at, is dictated by this rate. So this is telling us how fast you need to metabolize. And so your body is having to convert energy stores more quickly if you push the box across the room fast. That's the difference. That's why this tires you out. What turns out to be crucial for determining how difficult the task seems and how much it tires you out is how fast your body is having to transform the energy. And so this rate at which a work is done is a new thing we've encountered that's important, not only for you pushing boxes across the room, but for all sorts of other things. This is a power, and it is a work done over the time it took to do it. And if you look at these units, joules per second, we give that a name. 1 joule per second is 1 watt. And you will have encountered that before in other contexts. So just to recap, if some force is applied over some displacement, and so it does work, and if it does that in a time t, then the work that results from that force doing work is equal to some transformation of energy, right? In the case we just looked at, it would have been a transformation from chemical energy in your body to a thermal energy, but it could just as well be a transformation, say, from a gravitational potential energy to a kinetic energy, or just about anything else. But in any case, whatever this process is, where energy is being converted from one form to another, the power of the process is just the energy converted divided by the time it takes, or equivalently, if it's a force doing work that's causing that energy transformation, then it's the work divided by the time taken. And this applies to all sorts of situations, so while we developed it in a case of pushing something, you could equally well apply it to a case like a battery running a light, and now you have chemical energy stored in the battery being converted in the light into other forms. And I'll just say, people often say that light is energy. It isn't. Light is not energy. It's not a form of energy. However, it does carry energy. It has energy, and it transports it from place to place. And so we will often talk about converting one form of energy into light. Here's a useful shortcut for calculating power, and it really only works in simple cases, but let's look at one of these simple cases. So if you have an object that's being moved through some displacement, delta x, with some force acting on it, F, and let's say that force is in the direction of motion, and this whole thing takes some time, delta t. Then we know that the power is going to be the work done by that force divided by the time it takes. And in this simple case of the force being parallel to the displacement vector, that work is just the magnitude of the force times the magnitude of the displacement. But now look, if you just pull the force out front, you get this delta x over delta t. And as long as this is a nice straight line motion, then that right there is the speed. And so, at least in the case where forces are acting in the direction of motion for straight line motion, you can quickly calculate a power as a force times a speed. A light bulb gives us a very good example to look at the next idea that we're going to consider. So let's think about a 100 watt incandescent light bulb, and a lot has been made recently about how inefficient they are. So when we think about a 100 watt incandescent bulb, what we mean is that it consumes electrical potential energy at a rate of 100 watts. And, I put consumes in quotes there because I want you to be careful about how you think about that. No energy is being destroyed, it's being converted. So when we say a bulb consumes electrical potential energy, we mean it is converting electrical potential energy into other forms. But as you may know, it doesn't do this very efficiently if what you're looking for is light. Only about 2% of that, 2 or 2.5% of that energy ends up as light. And so you get a transformation at a rate of 2.5% of 100 watts, or 2.5 watts, as your power for the transformation from electrical potential energy into light, where I'll again caution you that light isn't a form of energy, but it is carrying energy away in various forms. And all the rest of that energy in the incandescent bulb is ending up as thermal energy. So a piece of terminology we often use is that the form of energy transformation that we want, in this case usually from the electrical potential energy to the light, is what we call the useful work for this process, whereas this thermal energy is called waste heat. And I'll just note, this seems very judgmental, but we use this terminology, and you sometimes have to be careful with it, right? Because in some cases you might not consider this heat, this thermal energy, to be true waste. For example, when you're using incandescent bulbs in Canada on a cold winter night, you might quite like all this thermal energy. I've already used the term efficiency when I was talking about that light bulb, and you probably had at least a vague idea of what I meant, but let's define it more precisely, because physicists actually use a precise definition for it. So many processes, like the light bulb or like pushing something across the room, result in this situation where you have some starting form of energy, like the electric potential energy for the light bulb or the chemical energy stored in your cells, in the case of you pushing something. And the process occurs and results in a consumption of that energy, some total energy transformation, and some of it winds up as energy in the form you want, or work done, that is the work you wanted to get done, and some of it winds up as waste heat. And whenever this happens, we can define what we call the efficiency. And you can think of it as the efficiency, E is what you get, right? The work that you wanted to have done, divided by what you pay, the delta E total, how much energy in the starting form you had to consume to get that work done. And so in terms of the symbols I've defined here, that would be the useful work over the total amount of energy transformed. Last thing I want to point out, and I've actually already done it if you look back at the light bulb example, is that when you're calculating efficiencies, it doesn't matter whether you work in terms of energies or powers. You'll come up with the same answer. So if we just take this formula for efficiency, that it's the useful work over the total amount of energy transformed, each of those energies has a power that you can calculate from it. So whatever this process is that's causing this transformation of energy, where some of it is becoming useful work, the amount of time in both of these is the same. And so if you calculate the efficiency using the powers, then each of those has the same delta T in it. And so those delta T's are just going to cancel, and you get back the same expression. And so it doesn't matter whether you work in terms of powers or energies when you're calculating an efficiency.